Hello, my name is Joshua Fair. I'm currently taking Physics 2211 at Georgia Tech, and this is my lab report. This lab discusses the constant velocity of the motion of an object and its relation to Newton's second law. Now, this lab discusses four key topics. The first being Newton's second law, which states that an object's acceleration is dependent on the net force being applied to the object and the mass of that object. In this situation, the object is going to be a tennis ball. The net force is the applied energy or force applied to that ball over a period of time. When the net force is zero, the ball is assumed to either be in rest or in constant motion or velocity. And constant velocity is a state when the ball neither speeds up nor slows down. It merely remains in motion at the same rate. Finally, this lab will use all of these concepts to examine how position and time are related when an object is at zero net force. The purpose of this lab was to use an object and demonstrate the before mentioned constant velocity and Newton's second law in both a lab and a real world setting. On the left is an image of a free body diagram of a ball rolling. Now, this free body diagram isn't exactly what we'll be using during the lab because it has two components that we won't be applying. The first is friction, as you see on the left here, and the second is an applied velocity. The ball in the lab is assumed to be at constant velocity or zero net force, thus these two components won't exist as friction isn't applied and velocity being pushed isn't applied. On the right, we have three formulas. The first is Newton's second law, force equals mass times acceleration. The second is the updated velocity formula. And the third is the updated position formula. We're going to be using the last two in our computational model that will be discussed later. Now here is the experimental model that we use to demonstrate the net force of a ball. We used Tracker for this and we recorded it. Now as you see, the ball is rolling and there's these little blue dots that as the ball is rolling. Now this corresponds to the data on the right. As you see, there's a graph that shows a downward trend, a downward slope, negative slope. This relates to position and time, and this relates to the Newton's second law, and we will be comparing this to the computational method in GlowScript as being discussed next. Now, we created this Python data in GlowScript, and the initial conditions of the method are shown. In particular, I set the mass of the ball to 0.5, as I wanted this to more closely relate to the mass of a tennis ball. And I set the original position of the ball to 0.00100. However, it came out in the code to round up to 000. I set the initial velocity of the ball to 0.800, negative 0.8. And I found this initial velocity by using the average velocity equation, thus resulting in the established condition. The delta t was found by me looking up the frames of my video, and it was 60 frames, so I divided 1 divided by 60. Now, this is the next section of my computational code. The formulas mentioned before that I discussed, the last two, are used in this code. The updated velocity formula is shown here, and it's put into Python so it can compute it. And the updated position formula is shown here. The ball has a constant velocity and thus no net force, as shown by the F net equals vector 0, 0, 0. And this is my code. Now, using this code in the previous tracker data, I was able to create a graph of time versus position using both the model position and the experimental position. This graph shows a pretty similar slope for both, a negative downward slope as time increases. However, the model position, or the one that I created in Python / GoScripts, is a little bit less consistent than the experimental position that I actually tested in real life. Now, I figure this is likely due to GlowScript rounding up the 0.001 for my position that I discussed earlier to 0, which would probably lead to slight differences among the two graphs. However, the data still conveys the same information of position and time having a negative correlation. So what if? What if we flip the axes? What would happen? Well, not much actually. The only thing that would happen is that the graph would have a positive slope instead of a negative one. And the data would still convey the same information as the one currently. And what does it mean? How is net force zero, and what are the pushes and pulls? Well, we technically can't figure this out because if the net force, for example, the friction is 1,000 and the velocity is positive 1,000, then it's still zero. But we don't know the exact coordinates or data. So this cannot be determined. Thank you.